assessment is hard under the best of conditions, and the testing stuff is partly there because the system doesn't trust the teachers to be
Yes.
able to do it.
Yes.
So the whole thing is riddled with stuff in there, and so we definitely, over the years, have searched for something as simple as the assessment a music teacher can make with a music student or a tennis teacher can make with a tennis student, which is somehow you have to have some situation that can happen over minutes rather than days, where the kid in some self-conscious way can show what they can do to somebody who knows what they should be doing. And so that is a tricky thing. And as I mentioned, one way we came about it was accidentally, which was through just making videos for the kids. The kids do take them
Sure.
home. But by having one of us as a camera operator and asking certain questions, we found that the kids could exhibit all kinds of knowledge in a completely unself-conscious way.
So this is a great tool for show what you know, what you've built, a concept
Yeah.
and things. But is it possible in this age of standards to align something like this to
California state
Well,
standards
I think you could make good standards. I don't think there's anything wrong with standards. I think you want to have some. It's part of this idea of having thresholds.
Sure. And
To
so
have-
we'll change the term then. So in other words, standards are nothing more than thresholds that the
But if I
children should
remember my
attain.
numbers correctly, California State Standard 5B in science, and they all start with the two-word phrase, students know. So 5B, I think, is students know that all matter in the universe is made from atoms. And science hasn't believed that for a very, very long time. It was only believed for a few years.
Sure.
And when scientists who were on the panel protested, they were told that, no, we're not going to, we've got our standards from the textbooks and we're not going to change the textbooks. So those scientists resigned. And those standards, by the way, were made in the 80s and they're still there. So when I hear about standards, my question is what are the thresholds for the standards? And if you take a real scientist or a real mathematician and you start looking at the standards, you find, ooh, these things don't feel, they don't appear like something that a real scientist would. In fact, they weren't done by and large by real scientists. They were done by, staff writers. They were done by textbook people. They were done by teachers, done by a whole bunch of people. And that's not to say that it's easy to do a good standard because, it's
Moving
like to
target.
catch a bird by pouring salt on its
Right.
tail. It ain't easy to do. And science is really tricky because what could students know in any modern sense about atoms? This is indirect knowledge. It was controversial even 100 years ago. The evidence for atoms is in 10 or so different tests. I've advocated science museums set up an atom room in the science museum where fifth grade classes can go in and spend half a day and be taken through things you couldn't possibly do in
Sure.
a fifth grade. So the problem is the very epistemology of science is hard to make happen in a fifth grade classroom, particularly if you decide that your fifth grade standard is going to be about things that were controversial 100 years ago that can't be seen. So Papert and the rest of us would just go, what? What you really want to do is let's drop some things off buildings and let kids like 10-year-olds like Tyrone, they can use their video cameras, they can take frame by frame, they can measure the things, they can make an e-toy model that exactly matches up to the physical
And
phenomena.
that model, I think, what a great example of showing.
So that was,
that
yeah,
revealing.
so the idea is if you're going to do science with kids, pick phenomena that's in their scale of world
Sure.
and figure out a way to do real science with it, rather than dealing with abstractions. And by the way, speaking about abstractions, you know, one of the abstractions that they put some effort into, I believe unsuccessfully, is energy. This is a tough one because it comes in many different forms and
Sure.
it's very difficult. And one of the nice things about these particle systems is that you can very often not have to make up an abstraction to do the mathematics because you can model the situation directly. So a thing that almost nobody understands even after college is why buoyancy works. You know, and they're told, well, it's the two different densities and the blah, blah, blah. Nobody understands this. But 11-year-old kid with 1 million particles
Mhm.
can easily make a little simulation that will do buoyancy just from Newton's laws, just from simple momentum exchange. And you all of a sudden realize where the upward force comes from. It comes in a container, it comes from the walls of the container. On the Earth, it comes from the connection of water all the way around the Earth. You have to have some place where it won't go sideways. And when it doesn't go sideways, that is when you suddenly understand that it's gravity pulling stuff down and things not being able to go sideways anymore that generates
Right,
these upward forces that will give you the momentum exchange. And it's harder to say than to do. And so I believe, you know, this is not one that Papert thought of, but to me, I always point to Papert as the true genius in this area of realizing, yeah, what you should be asking is what important ideas does the computer cut 10 or 15 years out of when you can introduce them. So one of them is calculus. If you've got a computer, you can do calculus with 9, 10, and 11-year-olds, the real deal, just not with algebra. Can't do it the way they do it in high school, but you can do real calculus because calculus has nothing to do with algebra. It's just the close it comes in.
Mhm.
And things like buoyancy is one of these things where you can just go directly at it. Or, you know, the pressure of gases and simple chemistry.